and what you do.
Sure. Thank you.
Take it away. Thank you.
Yeah. So I'm yeah, as you probably heard, I am a PhD in computer science. My experience is in NLP, kind of from a little bit more of a linguistics perspective, but I've done a variety of projects around kind of like applying machine learning to text and trying to either build explainable models of kind of linguistic competency or build benchmarks for AI systems to kind of test their performance and identify their limits. And today, I'm going to try to introduce NLP from a perspective that I think might be useful for people trying to do science, because I think that there is a strong tension between the culture in machine learning and AI and the culture in a lot of the kind of adjacent sciences that are trying to kind of understand something about the world. And I think there are a lot of interesting questions about how NLP can help us understand the world, understand ourselves, understand language. And they're very hard to answer. So I love to discuss that today and get some of your thoughts on it as well. So just as a very kind of brief scene setting, what is natural language processing? The way I would define it is something close to getting computers to do things with language. There are actually a lot of ways that you could define NLP. One way that I wouldn't is neurolinguistic programming, even though some people insist that's what it means. My kind of attempt at defining it is the study of how machines may perform tasks that demonstrate intelligence expressed through language or demonstrate linguistic competence and understanding. So this doesn't necessarily mean that we're trying to build AI systems that behave exactly like humans. It's kind of like what differentiates NLP from linguistics is similar to what differentiates AI from cognitive science. That the goal is to model some kind of like abstract behavior or competency, regardless of the particulars of how it's implemented by humans. Of course, then you have to define those competencies, and that becomes kind of a challenging point, but that is the starting point for a lot of NLP, where you can kind of think about doing NLP from the perspective of particular applications. So businesses might want to do something that's called sentiment analysis, which can mean actually lots of different things depending on the use case. But for example, if you have a product and you want to see what people think of it, maybe you want to troll Twitter and you want to see if people are saying positive or negative things. You might be a linguist and you're interested in like what kind of plausible computational mechanisms could explain how humans parse language, or you might just think it's interesting to see if we can produce machines that can reproduce that process of disentangling the meaning of sentences. And then there are a lot of things that you can do that are a very broad interest, I think, both to scientists and to engineers and to product developers, like building NLP systems that can translate between languages or that can answer factual questions by drawing on sources and really provide useful services to customers of services like Google. So basically, I think if you're putting language in or getting language out of a computer, it qualifies as NLP. Now, these days, NLP is dominated by machine learning. And there is a whole bunch of competition in the space of tools to use NLP to do stuff. So if you've ever tried to kind of get started in NLP, you might have been a little bit overwhelmed by the set of choices. In the collab, we're going to go through, I think, some of the kind of easiest starting points, which are going to be using tools from Hugging Face and OpenAI. So just as like very brief kind of historical background, Hugging Face is a startup. They've gotten a little bigger now, but they focus on open source tools geared at NLP researchers. OpenAI is it's kind of a nonprofit, kind of a for-profit. You've probably heard of it at this point. It builds kind of like big neural network models trained on massive amounts of data with the idea that they can be used for a wide range of services. PyTorch is a library for constructing neural networks and training them that underlies a lot of these things like Hugging Face and OpenAI. TensorFlow is Google's kind of version of that kind of computing library. And then FastAI and Spacey are a couple of other kind of like libraries for doing NLP that are kind of intended to make it easy to get started. But I think these days, the easiest way to get started is probably going to be with Hugging Face and OpenAI tools. And we'll see kind of what those look like in a minute. Okay, so if you want to do NLP, what do you actually do? How does it work? I would kind of break it down very roughly into 3 steps. You define a space of inputs, which are called X, and outputs, which are called Y, for some tasks that you're interested in. So the tasks I mentioned earlier, like machine translation, maybe you want to translate from English to German, or vice versa. Or maybe you want to do sentiment analysis. You just need to define what is it that I want the system to do, and I'll curate some data so that I can kind of like clarify my ideas, and maybe if I build a system that does it, I can test whether it does it well. The second step is implement a model for the task. So that's a program that takes in an input X and produces an output Y. And there are going to be lots of different ways to do that. The easiest way now is probably just prompting a language model with OpenAI. And finally, you want to test the model on your data and analyze the results. And that's basically it. That's what it looks like to do NLP. And you can often skip most, or well, probably not all of the steps, but there are a lot of tasks and data sets that have already been defined and are kind of out there for you to pull from the cloud. You want to make sure that you actually understand what's going on in the data before you use it for something or draw conclusions based on it. But you can reuse a lot of work that people have done. The models are often already implemented, especially if you're reusing an existing large language model. And the testing and analysis is the kind of thing that probably is going to be most interesting if you're trying to, use NLP for something. So yeah, in general, even if you're reusing some tools, you should always look at the outputs of the model that you're using and analyze it to try to understand, what is it doing? Is it doing what I think it's doing? That sort of thing. So yeah, examples. Maybe my task is going to be sentiment analysis with Yelp reviews. So I call it sentiment analysis, but the way I operationalize it is, I give my input is just a string that was written by someone on Yelp, and the output is the number of stars that corresponded to that review, right? So you're inferring something about the process that went behind writing that review. It could be interesting, for example, if you're a business and you're trying to understand, like, are people saying good or bad things about my business on a platform other than Yelp, maybe which doesn't have star ratings. Implement your model. As I said, Hugging Face and OpenAI are going to be probably the easiest tools to do this. Hugging Face if you're training a machine learning model on some training data that you want to use. OpenAI if you want to kind of just get started as quickly as possible. And then you test your data. So the way that you test the data in NLP is almost always going to be about predictive performance, which is maybe a little bit different from what you're used to with kind of regression analysis and traditional statistical modeling. What you really care about is the accuracy of your model at predicting the outputs of interest. How the model works is treated as more of a black box, and we'll get to that. We'll get to that later. But even if you don't know how the model works, you can manually inspect its predictions and the trends in its outputs to try to understand if there's like something going on there that you can make sense of, even if you don't understand the model itself. In particular, if you're kind of doing analysis on people and you have demographic information, that's one kind of thing that you can do is subgroup analysis, where you can say, does my model treat different subgroups differently? How does its behavior change on the basis of certain axes of variation in data? So these are things that you might want to be thinking about when analyzing the results. Okay, so again, I said this was intended to be kind of an intro for scientists. And I feel like you're probably aware, with OpenAI and some of these things, that NLP systems today can map lots of X's to lots of Y's pretty well. They're very impressive. You can do very cool stuff with them. But just because you can predict human behavior, does that mean that you can understand human behavior? And I think probably the people in this room are more interested in understanding human behavior, right? So, how does NLP help us? The models, you'd think they must have learned something about human behavior in principle, because you have to understand something about it to have high predictive accuracy. So how can we tap into that to understand something or learn something about humans? So that's the kind of question that I'm going to try and explore a little bit. And to start off exploring that, I'll tell a brief story. So, and this is a personal story. It begins in Palo Alto in 2019 in the basement of a 15-person house. I was sitting on my bed and I was scrolling Facebook, and I saw a post by someone who I hadn't talked to since high school. And in between waxing poetic about North Korean landscapes, he offered to narrate an audio book of a bootleg PDF that he had posted to his Google Drive of The Body Keeps the Score by Bessel van der Kolk. Who's familiar with this book here? Okay, so van der Kolk is like a well-known trauma therapist. He's really into this kind of like idea of like the relationship, like the physiological manifestations of trauma. And I was like, okay, I'm interested in this book. I'm curious what he has to say. I'll get the PDF. And I was completely floored by what I read in the introduction. And you might wonder what this has to do with NLP, but trust me, we'll get there. Okay, so in the introduction, van der Kolk describes his experience of working in psychology through the pharmacological revolution. So before kind of the 60s, asylums were a normal part of the public infrastructure. This is Pilgrim State Hospital, actually not too far from here in Long Island. At its peak, it held almost 14,000 patients. So these are kind of chronically inpatient, mentally ill people who are like, they can't really function in the world on their own, and they're under full-time care of like a huge kind of full-time staff. And this was normal. But starting in the 50s and 60s, this changed very quickly. With the rise of psychiatric drugs, particularly like the antipsychotics in the early days, a lot of people who were chronically kind of committed to these institutions were able to at least function to the point that they could leave and live normal lives. And over the next 40 years or so, what happened was this rapid process of deinstitutionalization, where like the vast majority of inpatients in mental hospitals kind of went off to society, and this was something that was totally like unprecedented. So the psychiatrists at the time were absolutely astonished with the results of these medications, where many of these patients were like completely intractable, and now suddenly they can lead normal lives. So you had this new technology, right, of psychiatric medications that had this crazy success, and it had a lot of kind of concomitants that went along with it in how the fields of psychology and psychiatry changed. So first of all, van der Kolk describes the systematization and consolidation of standards for thinking about mental illness, right? So the Diagnostic and Statistical Manual kind of became a thing. It became a lot more popular. It was used to standardize scientific study. It was used to standardize medical records. It was used to standardize insurance, even though in the DSM-3, it explicitly said it's not precise enough to be used for insurance purposes. That didn't last very long, right? Psychiatry really changed as a science. So van der Kolk describes how psychiatry departments were in the basement, and they started moving up until they reached the top floor, right? Because the psychiatry became the moneymaker. Why? Because you had clearly measurable treatments, right? You can exactly dose your medication in a way that is like easy to control and measure, that is not paralleled in traditional kind of psychotherapy and psychodynamics, that sort of thing, right? And it's marketable, right? You can make a lot of money with this medication. So it facilitated empirical science because of measurement, and it incentivized this kind of science because of the profit that you could make by working on it. And the result was this kind of huge boundless optimism about conquering human misery. So this is a quote from van der Kolk that like a lot of people at the time, when they were seeing these massive results, were like, we might have just solved the problem, right? We could potentially conquer human misery. So the upshot of this is a new way of thinking about mental illness that became dominant after the pharmacological revolution, which was the brain disease model, right? And one way of conceiving of that is that the cause of mental illness is an aberration of the brain, right? That this illness of the mind can be traced back to a physiological process in the substance of the brain. And if you treat the substance, you treat the illness. Now, how do we feel about the brain disease model of mental illness? Do we think it's good? Do we think it's correct? Who thinks the brain disease model is kind of correct? Who thinks that it's good? Who thinks that does it lead us to miss some important issues, do you think? So why is that? Because it's correct, right?
I mean, even like the enhanced status, right? I feel like like even today, if you ask anyone who's doing work in psychiatry, they know like it's not like it doesn't work for everyone. It's not one size fits all. Sometimes those actually like make people do different things. Like it's very hard to actually clearly measure it and reproduce it when like its effects on the person is going to change depending on that person and their own mental illness, right? So it's weird that from the beginning they were having this, but I think it was what you mentioned, right? The fact that it makes a lot of money is the reason why people were trying to make it seem like it is a for sure change and it's going to cure everything.
Right. And maybe it has fabulous results for like a certain subgroup that they were seeing at these institutions, but that doesn't mean that it's just going to solve everyone's problems. And like what you're pointing at as that like mental illness is just an incredibly complex process, right? And when you distill it to a dose of a pill, you make it measurable, but maybe in that measurement you miss a lot of what actually makes it work, right? So potentially by relying too much on the measurement, you're led astray from the underlying reasons for the condition, potentially, right? Okay, so that's that story. Now I'm going to tell you a different story. And this story, it's also has a personal element that begins in Seattle, Washington, where I did my PhD. I was working on NLP, and neural networks had kind of just become a thing. So they were really, really good at fitting any training distribution that you give them if you have enough data. So with enough data, the training loss would go down. It would be able to predict, it would do really well on a test set that was drawn from the same distribution as your training set. And it was like, wow, these systems can learn just about anything that we throw at them. And this wasn't true of NLP systems prior to that, which were basically like linear regressions. But the problem was generalization. So you could train it, for example, on like one data set of question answering, but then you ask it a type of question that it didn't see in that data set and it totally falls apart, right? So it's really overfit to the specifics of the distribution that you train it on. And there was this idea that like, well, we want to produce general systems. We want to produce systems that have some kind of general competency. But like every time we build a data set to try to test some general competency, it ends up getting hacked. So here's an example of that, a paper called Annotation Artifacts in Natural Language Inference Data, which analyzed a task called natural language inference, where basically you have a premise sentence, which is kind of like you assume the premise, and then you want to ask for several hypotheses, like are they entailed by the premise, or do they contradict the premise, or neither? And so this is just kind of a simple semantic understanding task where you know, here we have a woman selling bamboo sticks talking to two men on the loading dock. So it's implied that there must be at least three people on the dock because three people are mentioned here. Whereas because she's selling the bamboo sticks, that seems to contradict that she's taking money for the sticks, right? So this is the task. And in analyzing this task, what they found is that because of the way that the data was produced, you end up being able to do really well on this data set with really cheap tricks. So because the way the data was produced was you ask the annotators to take this premise sentence, and then you say, come up with something that contradicts it. It turns out a lot of the time, all they would do is add a not to it, and it would produce a contradictory sentence. And so in theory, like we're thinking about this task as like inference on language. In practice, it's detect the word not, right? So there's an issue of kind of, you could call this construct validity, I think, where the data doesn't necessarily capture the task that you want to do. And this is true in a more general sense, where these systems will catch on to all kinds of correlations that are a lot harder to see than just the presence of the word not. And so they solve your tasks in a way that doesn't generalize to new data. So how do we solve this problem? And I was recruited to help with this project called GLUE, which was a multitask benchmark. The idea being that like, if you test on a single distribution, maybe you're kind of like overfitting to the details of that distribution. But if you have a model which you can kind of like fit to a bunch of different tasks and do well on all of them, maybe that's representative of some kind of more general capabilities. So we had 9 tasks in this benchmark, and we're like, okay, your metric is actually your average score on all of them. And you could do some fine tuning on the different tasks to like, you know, you didn't have to have your one model perform all of the tasks at once, but you had to have one technique which allowed you to do well on all of the tasks, which maybe implies it gets some general competency. And we thought this would be really, really hard. And maybe it's hard, but what happened is progress on this benchmark just exploded. So within like, so we posted it on arXiv in 2018. We only got it into a conference by sometime 2019. And then by mid 2019, models had already passed human performance. And so like, how did they do this? It comes back to large language models. But before I get to the formula, the techniques, it didn't end with GLUE, right? Because what happens when we reach human performance, and I want to clarify something, it doesn't mean that the models are as smart as humans. It means that the models have reached the point at which our benchmark can no longer distinguish between them and humans, because our benchmark has some noise. So when your model's performance is good enough, your benchmark kind of becomes useless. So our benchmark went out of date very quickly. We made another benchmark. We updated it within like a year, and then that also went out of date within a year. In 2020, there was another benchmark called the Massive Multitask Language Understanding Benchmark that had 57 tasks. Now, with the release of GPT-4, the model is within a few percentage points of expert human performance on this data set. So it's almost the point of saturation there. In 2022, there was a collaboration called Big Bench, led by some people at Google, where they kind of crowdsourced from the whole research community, people creating new tasks. It's had 204 tasks, right? And some of the more recent models by Google are kind of exceeding average human performance on these tasks. So the point is like, whatever's going on in the NLP land these days is just crushing every benchmark and test that people can come up with. So it seems like we're producing kind of more general systems. What's the deal there? How does it work? So the formula looks something like this. This is what crushes all of the benchmarks. Step one is you take a big neural network and you train it to predict roughly all text on the internet. Step three, you win all of the benchmarks. That's basically what it looks like. Like it sounds like I'm joking, but like it turns out that if you train a model to predict all of the text on the internet, that contains a bunch of things as subtasks. So the objective that these models use is basically you just sample text from the internet, say a Wikipedia page, you give it some prefix of text that exists on the page, and you say, predict the next word. And in order to predict the next word well, like it turns out that you start picking up on grammatical patterns. You start picking up on world knowledge. Like if it says, if you have the sentence, Barack Obama was born in, blank, and it has to predict Hawaii, in some sense, it has to learn that like Barack Obama was born in Hawaii, like in some sense. Now, of course, we get very fraught in like, what does it mean to have knowledge? And I think these are very interesting and important issues. But the point is, this kind of training like encodes tons and tons of information in these models. And then once you have these base models, so GPT-3 is like probably the best known example of such a language model, you can do some fine tuning on them to basically steer them in the direction of being helpful or answering questions, that sort of thing. And that's how ChatGPT works. So ChatGPT is the first kind of model tuned with reinforcement learning from human feedback that's kind of publicly available, that is designed to kind of try and be helpful and nice and solve every task that you want for you. So for example, if you ask it how to bully someone, it will tell you it's never okay to bully someone, right? It doesn't just do the tasks that you want. It kind of tries to behave like a helpful assistant. And so far, this is kind of the MO of like all of the most powerful models these days, is you pre-train with like as much kind of sense data as you can get that encodes a bunch of information in the models, and then you fine tune them to kind of like output useful text instead of, if you just use the pre-trained model and then you ask it a question, you say, where was Barack Obama born? Probably say Kenya. So you need to do some fine tuning it depends on what else you say in the prompt. But the point is there's a lot of danger if you try to use those pre-trained models, because all they're doing is reproducing text on the internet. But they still learned a lot of the useful stuff. Okay, yes.
This might be like I've heard like, because there are a lot of people right now like trying to find loopholes, trying to make it say things that they shouldn't say, right? And apparently one way that they have like bypassed this thing of like avoiding offensive speech is like you create a character in the story. So like, so here's this person, Joe. He's like very, fascist, he's this way, he's that way. He wants to do this, like, what would he say? And then you guess to what like maybe the pre-trained models would be saying.
Yeah. And I mean, I think there are broader questions about like, what does it mean for such a model to be harmless? What does it mean for such a model to kind of inflict harm? You could even say like the token itself does not harm, right? It's bits, right? What harms potentially is the action that's taken on the basis of the token or the meaning that is inferred from the token. And so potentially if it says fascist things only on behalf of fascist Bob, that's not potentially as harmful as if it were to say those things unqualified in a context in which someone was simply trying to answer a question. They're just, I want to know where Barack Obama was born, not where fascist Bob thinks Barack Obama was born, right? So yeah, I think there are a lot of interesting questions about how should these models be steered. Any other questions? Okay. All right, so this is a revolution in NLP, like the way that like performance of the models have been growing. The models are incredibly useful. There's been systematization and consolidation of standards. So multitask benchmarks have become more consolidated. The models have become more singular, large language models that used to do just about everything. NLP researchers have seen their status as scientists a little bit enhanced. Everyone wants to get their hands on language models. I was invited to this room for some reason. And there's a ton of investment in these models because they're very useful for a lot of things that businesses want to do. And you also see some boundless optimism. So an official statement this is a quote from an official statement from OpenAI. If you're not familiar with the philosophy behind OpenAI, maybe this will surprise you. They say, we can imagine a world in which humanity flourishes to a degree that is probably impossible for any of us to fully visualize yet. We hope to contribute to the world an artificial general intelligence aligned with such flourishing. Colloquially, the way that they say it is, we are building God. So yeah, optimism. The upshot of this revolution, I would say, is the dominance of the deep learning model of artificial intelligence. Roughly speaking, that general and robust cognitive abilities arise in AI systems from training high-capacity predictive models and neural networks on as much diverse data as possible. So, do we think this is correct? Do we think it's good? And do we think it potentially leads us to miss real issues? What issues might we miss just by embracing the deep learning model of AI? Yes.
Because deep learning, well, basically, it's not that explainable. So I know there are some new techniques that people are trying to interpret findings in human brains and try to model them in neural networks, and I don't have the evidence that these models outperform rather than just simply put them through a very deep learning model. But I know some people may say there's some linguistic property in the human brain process, so we can put them in that model. So the model would first do some process and kind of bouncing around and using some concepts to predict rather than just using all the data to predict.
Right. Yes. So what you're pointing out is we have no idea what these models are doing, right? We have no concept of how they're performing the task. And so this question of generalization that I mentioned earlier, where, maybe it performs well in all the ways that we measure it, but what do we know about how it might perform in a new setting? That actually remains, right? Even when you tune your model to kind of try and answer questions factually, does that make it an authority on facts? If it tells you that something happened, would you take that as a trustworthy account, a trustworthy source in the way that you would if a human had said it? Still probably not, right? Because we don't have a good model of what's going on inside of the neural net. And just because it can predict well, it doesn't actually help us understand what the model's doing or the nature of the task, right? So that's a limit here. And as you might have been able to tell, there's a reason I told the earlier story about psychology, because we have a couple of revolutions on our hand, and I think that they have some things in common. Yeah, my alternative title for this kind of analogy when I've drawn it in the past is deep learning as a drug. But so how do we explain what's in common between these two things? I think one way of looking at it that's really useful comes from a paper by Leo Breiman, who's kind of one of the OGs in statistics and machine learning, who kind of bridge these worlds. And in this paper, he described what he called the two cultures of statistical modeling. So by statistical modeling, he means analyzing data about some process that happens in nature. So the way Breiman puts it, there are some kind of input variables X that nature associates through some unknown kind of black box process with some outcome variables Y. And there are two goals that we might have here: prediction of future Ys given some X, and information about how X and Y are associated with each other. So there are two ways to approach this. One is what he calls the data modeling culture. This is basically, you assume that the data is generated by a given stochastic model, right? So linear regression is a perfect example of this. You're basically saying, okay, assume this hypothesis space that only includes linear models, and then let's find the parameters that best fit the data. And then you can draw some conclusions, right? So you validate your model by checking goodness of fit, make sure that your data is actually linear, and then you can start looking at things like effect size and p-values and so on. And as far as I'm aware, that's what you're covering in this class. But there is an entirely different approach that Breiman is kind of partial to, which he calls the algorithmic modeling culture. And this is, again, you have the same thing about nature, but you don't assume anything about the process that's happening in nature. And you use whatever computational tools you have at your disposal to try to approximate that process as well as possible. And you validate your function just by its predictive accuracy on held out data. And you can draw different kind of conclusions from such a model. You can predict Ys from new X's. And this is how things are done in NLP. And so this is where I would draw the main distinction between what a statistician is doing in science and maybe what an NLP practitioner is doing in AI. Now, Breiman has some problems with the data modeling culture. And I think he's coming from where he's coming from is like the statistics world, where he says 98% of statisticians are data modelers. And this quote is really interesting. So I'll just kind of go through it verbatim, right? So he says, statisticians in applied research consider data modeling as the template for statistical analysis. When you're faced with an applied problem, you first think of a data model. And this enterprise has at its heart the belief that a statistician, by imagining and looking at the data, can invent a reasonably good parametric class of models for a complex mechanism devised by nature. Then parameters are estimated and conclusions are drawn. But when the model is fit to data to draw quantitative conclusions, the conclusions are about the model's mechanism, not about nature's mechanism. And so it follows that if the model is a poor emulation of nature, the conclusions may be wrong. So this is the classic issue of, if your data is not linear, your linear regression is meaningless, right? If there's a correlation in your data, but there's some causal variable that's missing, you might even learn the wrong causal relationship, right? That's Simpson's paradox. And this is true just beyond questions of like linear fits to quadratic curves, right? Because in any complex phenomena that you're trying to model, there are tons and tons of factors of variation that you're not seeing that could potentially confound the results. And when you assume them away, you limit your ability to kind of understand how they relate to the causal mechanism underlying it in nature. And it undermines your ability to kind of like actually draw conclusions about nature in general. I think this is like a big challenge for statistical analysis, right? And it's a great thing about predictive analysis is that, like, hey, you can learn models that kind of account for a lot more stuff than you can account for just by sitting down and thinking really hard about the hypothesis class. And then when your model does a really good job of predicting the outputs, you can be confident that it is capturing something important if your data is good enough. So there are still caveats, but yeah. So exactly. So here's how I would kind of characterize the world that we're living in here. Is there's a spectrum of approaches to data, ranging from kind of more theoretical, where you make more assumptions and qualitative judgments about mechanisms, and more empirical, where you make fewer assumptions about mechanisms. And they have different strengths, because the more empirical you are, the more confident that you can be that you're like modeling something that's closer to reality, right? Because if your assumptions are wrong, your conclusions simply will not apply. So you make fewer assumptions and your claims get to be stronger. The problem is that those assumptions actually also help you make a lot of claims. And if you want to make sense of any data at all, you need to have some theoretical assumptions. And so you kind of can't get by with only one or the other, right? Like if you only do the theoretical thing, maybe you're kind of in the Freudian land, which is like, doesn't necessarily go too well, because you need to be accountable to like the real world and the results of the treatments. And you need to use good experimental design and all kind of that kind of thing. Like, and okay, this is like very rough, like you can totally disagree with I'm just trying to get like an idea of what the spectrum looks like here. But if you're in kind of empirical clinical psychology research, then what you've got is like, well, you're applying a lot of methods where you have to make a lot of assumptions about generalization, where it's like, yeah, there's like no like singular mechanistically definable like thing you should say at any particular point in a session when you're trying a new technique, but you can kind of outline the process, you can kind of train people, you can create some sense of consistency and then assume that generalizes, and then you can do some quantitative study on it, right? Versus, you know, large scale psychopharmaceuticals, like you're just like, okay, here's my input, here's my outcome variable, let's see how they're related and like get as much data as possible and just hope it works, even though we don't really know why, right? And so I would say kind of the data modeling statistical analysis is still on the more empirical side of this whole spectrum, but deep learning is even further. Okay, so how can we kind of like get the best of both worlds, I think is the question here. And I think it's an open question. And it's something that like maybe we can talk about, maybe we can explore a little bit. But the way I would kind of try to summarize is, so algorithmic modeling and NLP, because of their kind of empirical nature, they give us this tremendous ability to represent and handle kind of the complexity of the world. But they don't, like on their face, help us understand the world better unless we can figure out how to combine them with some more theoretically motivated methods, right? At the same time, combining them doesn't just get you the best of both worlds, it also gets you limitations of both worlds, right? Because your predictive model might generalize in incorrect ways, it might not match reality, it might not be implementing the same kind of process as nature is, right? And so you really need to analyze its outputs to know what it's doing. And the conclusions that you draw on the basis of your theoretical methods will still rely on the assumptions that you make in your data model. So you kind of inherit all of the limitations, but maybe you have some new capabilities. And that's kind of what I think we could maybe try out in the colab, which I actually, because of the time zone mix up, I didn't 100% finish it, but there's plenty, we can work on it together, it'll be great. But yeah, so before we move to that, are there any questions or comments or thoughts? Yes.
Question. What are some issues or approaches in linguistics that lie on the spectrum you showed, and can we use machine learning to study language, e.g. language acquisition?
Yeah, absolutely. Absolutely. If you're interested in language acquisition, you need to kind of talk about like, what's the learning process that I'm studying? And is the language model like a good model system for that learning process? I think it comes down to like, if you're trying to draw conclusions about a phenomenon using like some experiment, you have to have construct validity, right? Like you have to be able to assume that your experiment is a model system where results on that experiment will generalize to the setting that you care about. With a large language model, you look at its linguistic capabilities, but it's seen more linguistic input than like any human would in thousands of years. Right. So like this idea, it doesn't really bear on questions about, say, poverty of the stimulus. Yeah, with respect to this spectrum, yeah, kind of Chomsky and minimalist syntax is going to be way over here on the left. And actually, like the reason I have so many thoughts on this is largely because of my experience with linguistics, trying to kind of balance these two worlds, where like I saw in linguistics, in the study of syntax and semantics, people are really interested in these big questions about how language works, and what meaning kind of looks like and what the right way of modeling it is. But like when the data that you query are kind of introspective judgments about meaning, like every kind of little experiment in formal semantics makes tons and tons of assumptions, right? You write a little toy grammar is what you'll do, and you'll assume that you're kind of that toy grammar fits into a larger picture. You assume that the toy grammar like embeds into a grammar for the whole language. You assume that like the grammar fits in with like a morphosyntactic layer underneath and then a cognitive layer kind of on top, right? Like you make all these assumptions about like the glue that holds everything together, and you focus on your like one little question that you're interested in about this particular quantifier and how it interacts with that thing. But the problem is, yeah, you're resting on tons and tons of assumptions in order for that conclusion to generalize. And in my work in formal semantics, which I kind of started off, like that's how I got into NLP, was through linguistics. Like I started to really doubt like the conclusions that people were drawing from this kind of study, because you would end up kind of arguing over different accounts of the same phenomenon, which all could potentially explain it, but then differed on kind of metaphysical grounds. And you kind of get into a philosophical argument. I'm like, there's no way to resolve this. And the problem is that you end up appealing to things like economy of expression, or like economy of the lexicon, or something like that, where it's like, this is an inherently statistical concept that if you wanted to make a rigorous argument on the basis of it, you would actually need a statistical model of the lexicon and the amount of information that's held in it. And so it's like, okay, can we start taking those theoretical questions, but then start applying like machine learning and data analysis to answer those questions better? But in NLP, that's not how it worked. In NLP, they're like, we just make data and then we fit the data and then we predict it and then we're happy, right? We're not trying to understand it. So I think that like in linguistics and NLP, there's also like room to kind of do work in this middle ground. And that's actually where I try to focus my work, which is, yeah, again, why I have so many opinions on this. But yeah. Yes.
Question. In cognitive science, a lot of work says that if we model the neural network after how the brain works, we'll do better at predicting human behavior with fewer samples. How does this idea apply to NLP?
Yeah. So this is getting at like a really kind of interesting and also very frustrating kind of historical debate in the field, right? So what we have people who are more theoretically minded, right? Who want to sit down and kind of understand the deeper structure. And then we have people who are more empirically minded, who almost as a matter of religion say we're not smart enough to like sit down and simply write down the theory of things. And these people clash with each other all the time. But the empiricists have won, both empirically and rhetorically, in that like the early methods in AI were people would sit down and try to figure out, okay, how does this work? And they would write down models, and then the models failed predictively. And AI has always been about this kind of empirical, kind of predictive mindset of, can you build a system that works? Because AI is inherently about trying to build systems that do things that we don't understand how to model. Like, it's kind of a trope. It's called the AI effect, that like once we understand something deeply, it ceases to be AI. So like a bunch of things like databases, programming languages, like search algorithms, a lot of this stuff that like today is thought of as just like traditional computer science actually started off in AI. And then once it became rigorous enough, kind of like wasn't AI anymore, because it was just math, or it was just computer science, right? And so AI is kind of inherently about like stuff that we don't understand how to do. And so you have people who are kind of insistent that we have to, well, you know, we have to like figure out how to understand it to make it work. But like, the people who think that and who succeed end up kind of not being in AI anymore. And then the people who are left who stay in AI end up kind of losing the battle to machine learning, which machine learning is also inherently about building systems to do things that we don't understand how to do. But I think another interesting point is that, as I said, they've lost the rhetorical battle against the empiricists as well. And the way that you can tell is, so I've covered the advantages and disadvantages of each side, right? The advantage of the theoretical side is that you can interpret the data better, right? It allows you to draw conclusions about the world. It allows you to understand how the system works. The advantage of the theoretical side is not predictive accuracy. But when you listen to people like Gary Marcus is like a prominent one who makes arguments along these lines. I don't know if Brendan makes these arguments as much, although it sounds like this is what you're saying he does it, is they argue like, well, we need to incorporate our understanding of cognition and so on and so forth in order to get higher predictive accuracy. And then they say, oh, because these models don't incorporate that stuff, they get this problem wrong, and they get that problem wrong, and they get that problem wrong. So there's like no end to these like op-eds by people like Douglas Hofstadter and Gary Marcus and that kind of thing, where they're like, the language model is never going to do this because it doesn't have this like underlying structure. And they kind of just get proven wrong over and over again. But the reason they get proven wrong is because they've already lost the debate when they say that the goal is to predict the outcome correctly, right? They've already kind of given it away to the empiricists at that point. Because like the truth is, as soon as you can kind of like give an example that the model, like that you think the model will get wrong, like, well, you can train on that example and it can get it right. There's this kind of whack-a-mole situation, right? Where like what the theory allows you to do is it allows you to get stronger guarantees about the model's behavior on data that you haven't even come up with yet. But then the moment you come up with the data, like it's subject to empirical optimization. And so it's a very kind of weird situation where I think theory has a lot of value, but I think the people who like theory aren't very good at arguing for it. But that's my hot take.
Comment. Sure, you can keep getting incrementally better performance by incorporating more data, but that data has all kinds of biases, and you're learning and solidifying more of those biases too. And the model can't show you why its predictions are correct or show you the biases and confounds. It doesn't really help you understand the data. But theory can help you do these things.
Well, yeah. So actually, I think that that's a great kind of case for trying to bring them together, in the sense that, like, if you want to understand the biases that exist in a large corpus of text, like a language model is an incredibly useful tool for doing that, right? You need to combine it with theory in order to interpret the data, but like maybe we can actually start discovering what the nature of these biases are, right? And start trying to kind of like work towards systems that at least are biased in ways that we prefer, right? Yeah, not to say that that's easy, but I think that like there's at least a case to be made for the language models having some use there. Like you can think of them, like I think it's tempting to think of them as kind of prescriptive artifacts when you think of them as like producing outputs that you're going to take actions on the basis of, right? Like classification model used by some business or something like that. But you can also think of it as a descriptive artifact of the corpus, right? And then you can start using some analysis techniques to try and like understand the corpus better using the language model. And also, even if it is biased, the thing is like it's so easy to use and kind of powerful that you can like start exploring data and start understanding the contents of data better despite the biases, at least as like a way of getting started on data analysis. Yeah. Yes.
Question. Where does the training data come from?
You mean for pre-training the language models? So nobody really knows where all the data comes from. I mean, basically they're training on like the entire internet and like books, and like probably they're scanning ancient artifacts and like training on those too, because like the more diverse text that you can train on, the better. Like they're also training on like all the open source code. So you have like coding assistants and that type of thing. Like it's not just language, like they're called language models, but they're really text models. And then some of them are now incorporating images and that sort of thing as well. So.
Question. If the training data is dominated by some domain where lots of data was available, e.g. social media text, will that affect how the model extrapolates to other settings?
Yeah, that's a good question. So like if you have a language model and you prompt it to engage in a certain kind of conversation, how will its training data influence how it engages in the conversation? So yeah, so this is kind of like the whole, I think one of the big conceits of language models is that like when you train on a huge amount of different and diverse data, you learn the factors that are kind of in common across your entire data distribution, right? So one could imagine, for example, maybe people have texted and they texted a lot about Donald Trump, but they never mentioned Barack Obama in their texting conversations. And now you simulate the language model and you ask it to engage in a texting conversation with you about Obama, right? And then Obama was never mentioned, but like you would expect that a good model should be able to engage in a texting style, but about a fact that maybe didn't appear in the texting context, but appeared in other contexts, right? So this is this kind of question of generalization from its training distribution.
Question. Is there some way of setting priors for the model, e.g. telling it what information is important and it should use to extrapolate versus what isn't?
So yeah, this is something that I think it's actually an active topic of research, and there are these ideas of like, can you kind of like erase a language model's memory? Can you kind of remove things from its training? Because you kind of can't, right? Like everything bleeds into everything else, and that's by design, and that's one of the reasons that they work as well as they do, because you need to incorporate information from all of the rest of your training data in order to generalize beyond like the small domain of, you know, whatever you're emulating at inference time, right? Like you need to be able to take facts from a wide variety of domains and then deploy them in the appropriate ways in that context. So I think there's a tension, and it's very much the same tension that's kind of like on the spectrum, right? There's a tension between modeling with full fidelity, like the process that you're trying to emulate, and like having some control over how that process works, right? Because the more control that you kind of exercise, the more constrained you are in what the model can actually do, because that control will impose assumptions that don't hold in the full data distribution. Yeah. Okay, any other questions? Okay, great. Then I guess we can I actually took up the whole hour with the lecture. I mean, we had the time. So I guess we can go to the collab. So has everyone made an account on OpenAI? Okay, great. Yeah, so that's one thing that we'll need to do is like you can make a free account and they get you like 20 queries per minute, which I think will suffice to do what we want to do today. Yeah, so I'm gonna kind of take you through like a very, I tried to kind of make as bare bones and kind of fun as I can of an example for like doing text classification with language models. And I think because language models are so flexible, it's like a good thing to have as a starting point, even though it's probably not what you would want to use in like the final version of a data analysis. Oh, yeah. I'm feeling dangerous. Okay, so the libraries we're using, so Hugging Face, as I said, it's like an open source toolkit, which is like pretty popular among NLP researchers. Actually, I'll just go to that. All right, well, I'll show you that in a bit. So OpenAI is going to be for prompting the language models, basically implementing our predictive models. Altair is like a really nice Python library for data visualization that I like using. I don't know what you guys usually use, but and then stats models will just help us compute some of the metrics, confidence intervals and stuff. So that's all we need for for it to work, now I can go through kind of what is Hugging Face. So this is kind of like a hub for lots of NLP resources. They have models that you can just readily kind of download with one line in Python. They have data sets for which you can do the same. So if you're interested in doing some kind of task, so for example, IMDb is like a data set of movie reviews from IMDb with their like sentiment labeled positive or negative. And you can kind of like browse through some of the data and get some of the documentation here. You can also search for various kinds of data sets. They'll usually have like a link to the paper that introduced the data set. So if you just want to start playing around with language data, this is probably like the easiest way to get started. Yeah, so Hugging Face also produces libraries that allow you to kind of load pre-trained models and then fine tune them in the process that I described earlier, if you have your own training data, or of course you can use training data from the hub. And that's for like, if you want to kind of get a little more serious about your modeling, although maybe GPT-4 is going to do better than the fine-tuned models anyway. That seems to be the trend these days. So, okay, so once we've installed our dependencies, yeah. So here you need to put your OpenAI API key. Okay, so I'm just gonna, I already loaded my OpenAI API key, so I don't need to do that. But you just need to put that in there and then run the cell. And that will allow you to make queries. So loading a data set is very simple, fortunately. So you just import this load dataset command, and it creates a dataset object, which is defined by the Hugging Face libraries, which gives you splits of your data. So data splits are very important. They're especially important for machine learning. I think probably more important than in like kind of data modeling style statistical analysis, because the predictive performance on the test set is like the measure by which you want to validate your data or your model. And if your model gets to see anything about the test set at training time, then like all your conclusions are kind of bunk. The situation is kind of funny now, because if we're using large language models, we're not actually training it at all, but you can still kind of let the test set leak into your design of the model, because there's still a lot of things that you can kind of design decisions that you'll make when using the model to kind of perform some task. So that's why we'll kind of start by focusing on the training set. If you want to explore the data, it's pretty simple. You just name the split, and then it looks kind of like a Python array, and you can just kind of see here we have the label is 4, and actually in this context, I think that means 5 stars, because they start at 0. And then we have the text of the view, and that's it. So it's a very simple task. You go from the text to the label, and so this next block just gives us some utility functions to kind of sample random indices from the data and show some items. So does that make sense to everyone so far? Is this kind of like easy to follow? We know what's going on. Okay, great. Yes.
Question: why do we need to use a training set with a pre-trained language model?
Yes, so you do want to have a train test separation. The situation is slightly different than it is with normal model training. The point is, like, you don't want any information leakage from the test set into whatever process you use to design your model. And so you still don't want to look at the test set, but when you're like prompting a language model, it might look, your training set might look more like what's normally called a validation set in machine learning. So actually, I mean, we'll get to this later, but I guess I can just say it now. So there are basically 3 splits that you usually have in machine learning. You have your training set, your validation set, and your test set. So your training set is what you feed into the algorithm that ends up deciding the parameters of the model. It's like the thing that you would run the regression on, for example. The validation set is the set that you use to decide model hyperparameters and to select which model you think is actually the best. And that's really important in deep learning. Like in linear regression, maybe it's kind of obvious, like, well, you just do the linear regression and you're kind of done. But with deep learning, neural nets can like fit all kinds of data distributions. So like when you train it on your training set, you might get a loss of 0. Like it might just perfectly fit your data, which is like definitely overfit to the training set. But for whatever reason, overfitting on the training set often actually doesn't harm performance like generalization performance for deep learning models. But what that means is looking at the training loss actually doesn't tell you how good your model is. What you want to do is you want to look at your held out set loss. So it's kind of like your pre-test set. It's like a pretend test set that you use while you're iterating on the model and deciding like how you want to implement it, what the hyperparameters are, so on and so forth. And then whatever gets best performance on the validation set, you say, okay, that is my model. And then you run it on the test set once, maybe twice, before you like publish the results of your study or your modeling experiment. So that's what the kind of NLP flow normally looks like. The thing that's different with large language models is you're not actually implementing an algorithm that like trains on your training set. You're just kind of like deciding how to prompt the language model and trying to improve its performance on the validation set. But you can just like treat the training set as your validation set for those purposes. So that's kind of what we're going to do. Any other questions? Okay, so what's next? Okay, so now we have our data. How can we create a model? The simplest way to do it is going to be an OpenAI language model. And the way that you use these models is actually just by sending web requests to their API. And language models are really weird and kind of fun. And if you've never used one before, then like there's no end to the kinds of things that you can try with these models. But the way that they're normally used for classification, so here, suppose we're trying to make a predictive model of like how many stars did this review have on Yelp, right? We need some way of basically instructing the model to perform the task and showing it what we mean. So first you just give it instructions, like you tell it literally, like, I mean, what do I tell it here? I say, please predict the star rating, number of stars, marked by the original author for each of the following Yelp reviews. It's like literally just like tell it what to do. That's like the simplest possible starting point, and it often works surprisingly well. Then you provide it some examples, right? Because maybe like it doesn't understand, like there's a lot of implicit stuff about like, well, what's the scale of the stars and like how many possible stars are there out of how many? Now you could say that in the instructions, but if you forget, or if there are other kind of implicit details that you don't have in the instructions, those kind of come through in the examples that you provide to the model. So it's kind of like a training set, except you're training it with like 3 to 5 to 50 or however many examples kind of fit in your query. But the more examples you use, the more expensive the query is going to be. Although in the scheme of things, it's not really that bad. Yeah, and then finally, you just provide it with the new input that you want to classify. So here, what I'm doing here is I create like a cache for our predictions, so that if we predict on the same example over again, we don't have to hit the API again, because OpenAI limits you to 20 queries per minute, I think, with a free account. So we just have a cache. And then we sample, 5 examples from the training set to use as demonstrations for the model. And then we can provide it the model. So we say, please predict the star rating, et cetera, et cetera. And then we just provide the examples that we sampled from the training set. And then we give the new review, and in the same exact format as we provided the example. So we have review, colon, review text, new line, and then stars, colon, space, right? And then the model is just going to fill in the gap. So it's still behaving like a kind of predictive language model in the sense that it's predicting the next token. But these models are kind of fine-tuned to try to like do the tasks that you're presenting to them in basically this format. So that's how we construct our prompt. Does that make sense? Any Python details that we should cover on that? Okay, great. And then the way that we run the model is we just use that prompt to make a request to OpenAI API. So Text DaVinci 003 is one of OpenAI's instruction following models. It's the strongest one that they had before ChatGPT. It's just trained to just do the task that you give it. It doesn't do any of the weird ChatGPT stuff about like refusing to do the task and like engaging in dialogue or whatever. So it's kind of like one of the classic ones to go to for classification, even though it probably would be a little lower accuracy than ChatGPT. So all you do is you just use the OpenAI completions endpoint, you create a request, you give it the prompt. And the kind of one important parameter here that you give is temperature. So temperature it's a technical term. but it basically corresponds to the level of randomness that you want. So when you generate a text completion from a language model, the way the language model works is given some prompt, it produces a probability distribution over the next token. And then you can sample from that probability distribution using different strategies. The temperature parameter is the temperature of the softmax distribution that is used to determine the temperature of the softmax that is used to determine that probability distribution. Is everyone familiar with like softmax distributions?
We don't, just briefly about.
Okay, yeah. Basically, you can think of it as like a sharpening or a flattening of the distribution, where a temperature of 0 will just output the most likely token every time. A temperature of 1 is kind of like the normal softmax, where you sample from the probability distribution that the model kind of natively learned. And then if you increase a temperature above 1, it pushes it to be more and more uniform. So it's more likely to sample stuff from the tails. So if you're just doing classification and you kind of want to get the best outputs, like you probably would just use a temperature of 0. But if you're doing some kind of maybe more creative task where you want to be able to sample repeatedly from the model and get a bunch of examples, you would want a higher temperature so that you can get some diversity. It also will generate more interesting text. Like if you want to generate stories or that kind of thing, like you would not want to use temperature of 0. It would produce very, very uninteresting text that focuses on like high frequency words and very boring statements that kind of don't mean anything. Yeah, so that's our model. I mean, I think it's actually just kind of insane that like literally this single block of code gets you like a pretty decent predictive model of a new task. Like this has not been true for that long in the NLP world, right? But basically what we want to do here is we want to produce a function that's basically our predictive model here, where it takes the input text as a string and it outputs the label that we want. And so what we do, of course, yeah, we have to handle the cache, but we just make the query to the API. We will get the result from the API response, and then we will convert it to an integer. And if it happens not to be an integer, we'll just return 3. That's one thing that's kind of weird about these models is their output space is actually just all of like tokens. And so they're actually quite good in general at outputting something that you want, especially if you provide demonstrations. But when I was testing this earlier, I had the error throw because the model put 3.5 and I was like, I guess. but that's not actually part of our label space. So it's like, okay, maybe we should round, like you could potentially improve this, but it's not too important. So here we can kind of see what that looks like in practice. So we sampled kind of 5 demonstrations for our prompt, and here's what the prompt looks like. We have our instructions, please predict the star rating, yada, yada. And then we have each review on a line. And of course, this kind of goes off to the right pretty long to include the whole line, and then a new line, and then the number of stars. And so each of these was drawn from the training set. And then here's the new review that we're classifying. It says stars, and we're just asking the model to fill in what's here. When we make the request to the OpenAI API, here's what it returns. This is like just mostly some metadata. The thing that we really care about is text in kind of the top choice. So that's what I kind of get here. I just go choices 0 text and then convert it to an int, right? So that allows us to do our simple classification. We output 5. Okay, now we have a model and we can assess how well it performs. I already said the stuff about training and test. I'm actually being a little bit sloppy here because like it kind of, yeah, you would want to be like very careful about how you're partitioning your data in a proper data analysis. But when we're doing something quick and dirty, just try to understand the data. It's not too important, especially if we're just not touching the test set. You can kind of do whatever you want with the training set. But what I'm doing here is I just have a function for evaluation, which takes in our model, which is again our function from input to output, the indices in the data that we want to evaluate on. And I have an option to include all of the cache predictions that we've already run so that we can get more statistical power on our results. So all that's going on in this function is we're deciding which indices in the training set we want to predict on. We get all of the inputs. we get the gold labels for them, so from the data set, and then we run the model on each of the inputs, and we get its outputs. And then we can just compute its accuracy. We can compute a couple metrics for this task. We can compute accuracy and also absolute error, since we're predicting something that's like an integer. So I think this is fairly straightforward. We can get confidence intervals using stats models, just because we're running with very small data, because again, like limits of the OpenAI API. Yeah, so it's always good to compute what results you can, print out like some examples. So here are basically going to be some error cases of the model, and then a confusion matrix of how the model did. So what does that look like for us? Yeah, I've run this a few times, so I've kind of cached up some results. With this prompt, I get an accuracy of like 64%. It's not super high, but the mean absolute error is actually decently low, right? It's like 0.37, which means we're like less than half a star off on average, right? And even with just 188, the confidence intervals are enough to kind of be like, okay, these numbers are kind of reasonable. And the truth is, you could probably do a whole lot better if you just kind of iterated a bit on refining the prompt, doing a little bit of error analysis, maybe including more demonstrations. Like honestly, you can probably fit like 50 demonstrations in there, and it would probably do better, but it's just harder to see for demonstration purposes. So here we can kind of see some examples of mistakes. So I actually, yeah, I wonder if I have an off by one error somewhere. It's possible, but you know, we have amazing, that is all, the meatball sliders are the bomb, pizza's delicious, sorbet and all this are winners, and they gave it 4, it seems. I would have expected 5, so you know, the model seems reasonable here. It's possible that there is an off by one, because the labels, let me see, what did I do here? Oh yeah, here I added one. I added one to the labels, so I think that should be right. But anyway, yeah, and we can see in our confusion matrix that the model seems to it seems to kind of like not be relatively unbiased, right? So the confusion matrix is around the diagonal, meaning for each of the number of predicted stars, mostly it centers on the actual number of stars, and there isn't a super obvious bias one way or the other. So it's kind of amazing that you can just like ask a language model to predict the Yelp stars, and it's like kind of calibrated, even if it's not perfect, right? And then sometimes the Yelp stars are like, so, you know, I guess this gets back to construct validity. Can you really predict the number of stars from the text of the review? Yeah, so that's something that can be worth looking into. Okay, any questions about this so far? Any thoughts? Yes.
Question. Is there anything special about how language models are constructed compared to other neural network models?
Yeah, so the differences are shrinking by the day. I would say like the clearest and least kind of distracting way of thinking about these models is as black magic, which like I think a lot of people don't like. I don't like it. But the truth is, like, the algorithmic modeling culture is like deeply embraced in machine learning, where like simply it's a matter of mapping from inputs to outputs. And there are people who deeply understand like the mechanisms that are at work in the model, but the connection between the mechanisms of the model and like its actual behavior is really hard to determine. So the architecturally speaking, the way that these models work is in a lot of vision models, they use convolutional neural networks, as you mentioned, which have operations that are translation invariant. So it's like if you want to detect the presence of an object in an image, maybe you want to execute a function over a bunch of different patches of that image and then aggregate the results. And convolutional networks are like constructed to kind of do that a priori. For language processing, one of the challenges is linguistic input is kind of discrete. So in image models, you can kind of treat the inputs as RGB channels. And so these are numbers, which you can then feed into kind of matrix multiplies and stuff. But in the context of language, like what is kind of the brightness value of a word? What you end up doing is you embed words in the vector space. So each word, and actually it's not technically the words which have vectors, but that's like another implementation detail. But each word will basically have some n-dimensional vector. So maybe it'll be 768 dimensions, maybe it'll be, 2000 something dimensions, that is then fed to the input layer of a big neural net, which it's not convolutional over the length of the sequence. So that it uses an architecture called transformer, which basically, if you imagine the sentence as kind of a bag of vectors, what the transformer does is it looks at every pair of vectors, and it has like its representation, which starts off as just the word vectors, right? And it computes like some kind of association between them. And based on that association value between them, it kind of mixes their values together according to some like operation. So this is it's called a multi-headed self-attention. If you wanted to kind of Google the term, this is kind of the like core operation underlying a transformer, where yeah, like I could give an intuition about, like, for example, if you think that, like, if I wanted to say, something about like Barack Obama, right? Again, Obama is a very common example for whatever reason. Even after Trump was elected, we kept using Obama examples. But so if you have like the word Barack and then you need to predict the next word, probably Barack is very informative of the next word being Obama. And so you would expect like the model is going to kind of have to pay a lot of attention to that word. And so the attention operation kind of helps you kind of decide which parts of the sequence are salient. And so a lot of people have kind of made careers out of staring at attention patterns inside of models and trying to say something about what they're doing. The problem is actually conclusions drawn on the basis of staring at those patterns are not very robust. And so we have an intuition, right? It's called attention. There's an intuition that like, oh, there's this latent operation within the neural network where at each node, it's kind of looking at the other nodes, deciding which ones are important, and then propagating some information. But like actually the information flow is a lot more complicated than that, because everything kind of gets mixed up together in between layers using multi-layer perceptrons as well. And yeah, so it's actually really hard to say what the model is doing on the basis of the architecture, except that it is a very general architecture that can express lots and lots of different operations, and so that allows it to learn a very expressive function. You have like a bunch of text, and then informing the representation of each token, it kind of incorporates information from all the other tokens. You can think of, I mean, if you're familiar with n-gram models, you can think of it as like a really fancy kind of like matrix factorization of an n-gram model. Yeah.
Question: how did they come up with these architectures? My understanding is that they were often inspired by our understanding of the brain and cognition.
No, that's absolutely right. Yeah, maybe I underrepresented the kind of role of theory in driving our intuitions, because I think that like in a lot of cases, people kind of, they would analyze the failure cases of existing models and they would say, okay, it's probably not working because of, like with recurrent neural networks, the problem was like vanishing gradients, where if you have a representation that's like a memory that's kind of held over time and you incorporate information from each token and you have to hold on to that memory, then like you can't like propagate the signal backward in time through the sequence. And so this was like a problem with recurrent neural networks that people tried really hard to solve. And yeah, it was based on this theory of what was going on that they did it. With transformers, like, so here's the thing, like the thing that really made transformers work, like you could argue that it might have had to do with attention, but like attention in transformers is not really that related to like neuroscience or cognitive concept, like versions of attention. It was designed to kind of solve a technical problem of representing sequences of non-fixed length, where like prior to attention-based models, the way that people would try to learn to do machine translation is you would take a sentence and then you would smush the sentence into a single vector, and then from that single vector you would like decode the sentence in your new language. And this is just like, there's a massive information bottleneck there. So then the question is, how when I'm decoding, can I just open up the information bottleneck and allow the model to kind of incorporate as much information as it needs from the kind of input sequence? And this was what the attention operation was designed to do. So it's kind of like is it intuition about cognition? Is it intuition about like the particular problem? And then the reason that attention or that transformers work so well for language models is just because they're parallelizable. They train well. Like it's just the engineering works out. And that actually is like one of the biggest factors behind a lot of the progress in NLP is like we have GPUs which can do matrix multiplies really fast. We have like models which train well, which take advantage of these matrix multiplies, and we have massive amounts of data. And so like in terms of like what was actually instrumental in getting these things to work, it mostly was like you have a lot of people thinking about these kind of cognitive questions and the answers mattering less than the engineering constraints and scale. Yeah. Any other questions? Okay, so that was maybe a little bit boring, but I think we can get a little bit more creative. And so, okay, and this gets towards like this issue of bridging NLP and science that I was talking about earlier. So how can you use a predictive model to try and understand your data or understand a phenomenon better? So I'm thinking like, maybe we're curious about the relationship between like the number of stars in a Yelp review and the emotions expressed by the author of the review. If you're interested in this question, how do you think you would investigate it if you didn't have computational tools? Like probably you would just kind of like sit down, stare at a bunch of data, think about like what's like an appropriate way of coding this data. What are like the underlying processes that I want to capture with the data? These are all things that you absolutely should be thinking about in order to do good science. But now you can do lots of engineering and data exploration before you even do any good science, which might help you decide whether to invest more time in that at all, right? So first of all, you can maybe find some existing data sets that have labeled data for like kind of emotions that are expressed in text. But like, you don't even necessarily need to do that, because with language models, you can like just totally come up with new tasks on the fly and just instruct them to do something like a little bit more creative. So here I have some code which kind of mirrors our earlier code to just predict the emotions expressed in text. So I say, please describe in a single noun. And this was originally in a single word, but then when I looked at the output, some of them were nouns, some of them were adjectives. And you had like disgust and disgusted. It's like, these are the same. So you find you often have to refine your prompt to kind of steer the model to do what you want, right? Please describe in a single noun the most prominent emotion expressed in the following Yelp review. Be as specific as possible. So here I'm not even providing demonstrations because I'm curious what the model will come up with, right? Like I want it to kind of be creative and basically I'm having it do my like qualitative analysis for me in some way. And I don't have to trust it, right? Like I can always go back and check what it's doing, but if I check what it's doing and it's like kind of reasonable, then like it gives me a handle, at least a starting point for thinking about what kind of stuff is in this data, right? So given that prompt, I can generate and like I can just create a new request, generate like an emotion, and then turn that into a predictive model. So there's a little bit of plumbing here to kind of cache our predictions and try and share examples with the prior model. But it's not too important. The point is we now have a model like very easily constructed that predicts the emotions expressed in text, whatever that means. I didn't even have to define it. It's kind of silly. But the point is you can do it. And right, okay. So all we're doing is running the model on each of the target indices and then logging a little bit of metrics. So here we don't actually have gold labels. So what we want to do is we just want to understand what the model is doing. So we can print out like the number of emotions that it used, the set of emotions for the inputs that it got, and then just like histogram, like what are the most prominent ones in the data. So let's see, the emotions I got, I don't know. I mean, I was actually surprised with the diversity and kind of the expressiveness of the words here. So we got astonishment, disappointment, discomfort, discontentment, disgust, disillusionment. Yeah, and probably you guys got like a very different set of emotions than I did, just because like we're running on like very tiny random samples of the data, right? So we can look through and we can see some examples. Always important to look through and see your examples. So like here we got food poisoning and and the emotion is discussed. Right. Or, loud, service sucked, waiter should have paid more attention. I asked for this. And then, dude, I'm still freaking eating. So this person is irritated. That's not wrong. Right. So it's like the model seems to be producing like reasonable words in a lot of these cases. Right. And that's the thing is like, you can like this model is almost certainly going to be fooled by a lot of weird cases. It's almost certainly going to be biased. It's going to almost certainly have like some subset of its outputs that kind of don't make any sense. But like, if you just average, the average probably is going to be roughly representative of what's in your data. And so I think it can be really useful for data analysis for that reason, right? So yeah, let's see. We got, pride. That's kind of interesting. Not any place I can think of in Las Vegas to get a bow the caliber that you get a great bow. Oh, here we go. Jenny went to Cal just like me. Yeah, okay. So he sounds a little proud. Sure. Right. Yeah, right. So you actually get to see a lot of the kind of diversity in the data this way. And then a brief little histogram we have here, which is, it seems disappointment is quite prominent. And the others are fairly diverse. But I mean, maybe maybe I already have learned something about Yelp reviews. Like people tend to like go onto Yelp and write reviews when they're disappointed, right? So what I just did is I just generated a hypothesis, right? Which now if I'm like curious, like, oh, what actually drives people to write reviews? Is it disappointment? Is it frustration, irritation? Like now I can kind of begin thinking about how to explore that question. I've already kind of like formed a hypothesis. All thanks to Stochastic Parrot. So yeah, I actually haven't finished the rest of this, but I can tell you what the idea was, and maybe we can work on it together if you're interested, is maybe we want to draw a qualitative conclusion. So the qualitative, or actually quantitative conclusion. So what we can potentially do is look at each of the emotion categories. Excuse me. We can look at each of the categories of emotions and then ask, what are the star ratings of the emotion of the reviews that express that emotion? And what's the relationship between the most prominent emotion expressed in a review and the rating that the person gives? And then maybe like, if it's always nice to like kind of scientifically investigate an obviously true conclusion, right? We could use one more model and basically say, okay, can we map all these emotion words onto kind of a valence scale, and then just do a regression, right? Just do a quantitative analysis of what's the relationship between the valence of the emotion that's expressed and the star rating of the review. So that will be maybe the challenge for the last 20 minutes. But I think one thing, the main thing that I think is interesting to discuss is suppose we did do that, right? Suppose we did that regression and we came up with like, we had like a p-value, like a nice p-value that was like, oh yeah, like more positive emotions that are expressed in the review correspond to higher star ratings. Is there anything wrong with me drawing that conclusion on the basis of what I've done here? Like, sure, forgetting that it's obviously kind of true, probably. I guess you never know. Like, why should I like pause before stating that conclusion? What are like the potential reasons that it might be wrong, or that it might not be justified, rather, on the basis of the analysis?
Comment. Perhaps we wouldn't get a significant result because most of the emotions expressed in the data are negative.
But suppose it's significant. And then I say, aha, like reviews that express positive emotions are more likely to have higher star ratings. Is that conclusion justified even on the basis of a significant result? Like, and what are the reasons that it might not be? So, okay, one is this model that predicts the emotion, like I didn't validate it on anything, right? Like I looked at it and it's like, okay, it's pretty good, but like, who knows what its error rate is, right? And also, wait, what does it mean to like predict like most prominent emotion? Like maybe there are many emotions that are expressed in a review, and like maybe there are some biases in which one the model chooses to highlight, right? Or maybe the model just like outputs kind of like weird stuff. a lot of the time, and I just didn't happen to see it. So this is, I think, what you'd call internal validity, where like your model isn't even doing the thing that like that you're like testing, that you're measuring it to do. Another problem is like, even if the model is doing a good job accuracy wise on like predicting prominent emotions in the text, I mean, what does it mean to predict the emotion expressed in the text? And what are the features that the model is using to decide that? Because suppose I was doing this out of domain and like actually I was testing the relationship between predicted emotions and predicted star ratings. It could be that there's a strong relationship between the two, right? But if there's a strong relationship between the emotions and the star ratings, it could be that your model of these star ratings is actually just modeling the emotions and then extrapolating the star rating on the basis of the emotion. And if that's true, then the connection between these two variables is going to be amplified because of my reliance on the model, right? So like the outputs of the model might actually be more correlated than the underlying variables because of a failure of the model to like accurately reconstruct the process underlying like the data that we actually care about, right? So even if your model is accurate on the whole, it might have error patterns that are biased in favor of one conclusion or the other. And I think this probably would fall under what you'd call construct validity. Finally, I think there's the issue of external validity. So if I say like the model, right, my conclusion was that reviews that express positive emotions, prominently express positive emotions, have higher star ratings. Maybe if I have internal and construct validity, that's literally speaking justified on the basis of like the data that I've collected, right? But when I say have higher star ratings and when I say more prominently express positive emotions, I'm talking about two things that I very specifically operationalized in this experimental setting. But like higher star ratings on Yelp might be like different from star ratings on some other platform. They might be different from star ratings outside of this particular Yelp data set that I used. There might be different ways of operationalizing what it means to prominently express an emotion that depend on the setting in which like the expression is happening, right? And so maybe I've drawn a conclusion about the setting in which I did the experiment, but does that generalize into an insight about like the processes that are underlying the domain that I was studying or the process that I care about learning about as a scientist? Maybe not. And so you need to make an argument about the generality of your experimental setting to the ideas that you care about. So that's external validity. So that's another thing that you have to worry about. And then finally, of course, you have the data modeling issue of like, well, you modeled this as kind of a regression, and like maybe there's some like deeper relationship between kind of the emotion being expressed in the review and the star rating that kind of is like a better way of thinking about it. And like the conclusions that you draw totally depend on the assumptions that you make about the directions of causality there. So, but that's like you normally have that problem with regression. So I'm sure you're used to that. But the point is like you can do all kinds of magical things now, and it's very cool. But then you have even more caveats on like the analysis that you would want to do at the end of the day. But I think it's still like a great idea to just play around with the data, see what you can kind of predict and do, and have fun that way. But yeah, okay. So I think that's like covers everything I wanted to make sure that we said. And I don't know if we end at 10 till. Okay, great. But so we have a couple minutes, I guess, for any questions if anyone wants more. Yeah.
Question. Suppose we went into much more detail to write a more specific and better prompt. Could we then have more confidence in what the language model is doing?
So your confidence in what it's doing should only be based in its performance on data. Like, yes, you can like write better instructions and kind of be more confident that it will do better. And like it usually will, but again, treat it as black magic. You never know what the model is doing, why it's doing it. And what you're doing, you write your prompt is you're writing magic incantations in like a secret language that like, right, you're not speaking to a human, you're speaking to like a being from like beyond the veil. Like this is like intuitions need not apply. So, but that said, yes, like you can certainly give more descriptive prompts, especially if you have like bullet points of like basically things that should be pretty easy to verify and you have like a bunch of those. then the model will often be able to kind of like adhere to the constraints that you give it. If it is too long, then the model might not be able to keep track of everything that you told it. It depends on the model as well. I think that like ChatGPT and GPT-4 are going to be a lot better at handling these like very, very large prompts. Like, I don't know if you saw any of the hype around like Bing. It turns out that Bing seems to be basically GPT-4, but with like this massive prompt that gives it a whole personality and everything, right? And so it's like you can potentially do that kind of thing, and you can expect maybe better behavior out of the model. But as you're developing the prompt, like you should always be checking that the behavior is updating in the way that you want. And yeah, there is a limit to the length of the prompt. It's like a technical limit. I think, I don't know, it depends on the particular model. I think usually it's around like 2,000 words or something. So it's like actually pretty long. And so you can fit like tens of demonstrations in there at least, usually, yeah.
Question. So how do you actually know or figure out how to prompt a language model better?
So this is like a big question, like in NLP literature that people have struggled with, is like when you're measuring the performance of these models on some task, it depends how you prompt it. And then you have problems of overfitting. So what people would do is be like, oh, wow, the model like learns how to do the task based on only 3 examples. But they selected those 3 examples based on development set performance with a development set of size like 200. So it's like, actually, it's kind of using 200 examples to decide on 3 examples. So it's like, how much? Yeah. So it is kind of a dark art. And like some people are kind of like working on principles to figure out which demonstrations are better. Like, for example, if you use demonstrations and instructions which have higher likelihood under the original language model, then it tends to perform better on your task, for example. So there are like some kind of like rules of thumb that like honestly are probably going to be too much pain for you to implement in practice. But yeah, this is like a big open question in the research field, is like, how do we even study these things rigorously? Yeah. Okay, cool. Thank you, everyone.